Right, I'm going to go through two sets of core practicals in this video, rates and electrolysis, just because we've done them both relatively recently, so I think I can hopefully get them done nice and quickly. First one we'll do is rates of reaction. So I've got an equation here, and you could get asked, design an investigation to show how you would measure changes in temperature on rate. So if you want to investigate how temperature affects rate, you need to be able to measure the rate of a reaction. Because this particular reaction is producing a gas, you've got two choices. You can either use a mass balance and record the loss in mass over time. Okay, the gas will escape. So if I'm starting off with 50 grams of reactants, I will get a decrease in mass if one of my products can escape. So record that change in mass over time. Or your other option is to capture the gas as it's being produced in a gas syringe and record the change in volume over time. You could be asked, I mean they haven't, but they could ask you for an advantage or a kind of a disadvantage comparing the two methods. If you're looking here at the mass balance, your change in mass is going to be very small. So you need to have a balance with a very high resolution that will allow you to detect those really, really small changes in mass. Especially you're recording it over time. So every 30 seconds, you're going to need to write down a new mass. And even though the gas is escaping, the change is going to be so small that if you don't have a high resolution balance, you're not going to be able to record it. Your disadvantage over here with your gas syringe is you need to mix the reactants together and then add the seal with the gas syringe. And in the time it takes you to replace that seal, even if you're speedy, you are going to lose some gas. So you're going to lose a little bit of product in the time it takes you to replace your seal. But this is experimentally how you would do this reaction to measure the rate. But if I want to investigate temperature, I need to make it a fair test. So what would I keep the same? There's a number of things you can say, but just avoid using the word amount. So if I'm talking about magnesium, rather than saying the amount of magnesium, because it's a solid, I would say the mass of magnesium. Also, the size of the surface area affects the rate. So I would say use the same sized pieces. If you want to talk about the acid, again, avoid amount. It's an acid, so it's in solution. So you can say use the same concentration, you can say use the same volume, you could say use the same pH. But you'd keep that the same, you'd change temperature, and to actually measure the rate, you would describe this method. Then once you've actually got your results for temperature, I mean, you should see something like this if you were to plot it on a graph. So I've got two peaks here. I've got 20 degrees and I've got 40 degrees. And you can see that the 40-degree one is steeper to show me that it's faster, but that they both level out at exactly the same place. This tells me that the yield is the same. Okay, so remember, if you're baking a cake, baking at a higher temperature doesn't give you more cake, you just cook the cake quicker. So both of them should level off at the same point, and I'm saying they both produce 50 centimeters cubed in total. Okay, but you can see here that I'm able to hit 50 centimeters cubed after 2 minutes at 40 degrees, whereas it takes 8 minutes to get there at 20 degrees. So I can say the yield is the same, but the rate is faster at a higher temperature. So anytime we're talking about rate, we are talking about speed. And if you're talking about speed, you need to reference time. So think about it, meters per second or miles per hour. You're always referencing time when you're talking about a speed. And it's the same with rate. When we're explaining why the rate is quicker, we need to reference time. And we do this by talking about the frequency of collision. So frequency is a reference to time. Now, if you increase the temperature, you are increasing the energy, and if they've got more energy, they will move faster and they'll collide more frequently. So I just put, I mean, I obviously just made these numbers up, all right? Let's say at low temperature, you're getting 100 collisions per minute, but at high temperature, 200 collisions per minute. I can say the collisions have become more frequent, particles moving faster collide more frequently. But the other thing that you need to mention is the activation energy, all right? Remember, it's not enough for them to collide, they need to collide with sufficient energy, and that is called the activation energy. So even if you've got 100 collisions per minute, let's just say only 20% of them are actually successful, because a lot of the particles don't have enough energy, they collide and then they just bounce back off each other. But if you increase the temperature, not only are they colliding more often, but because the particles have more energy, more collisions will actually result in a reaction. So I'm going from 20% success to 40% success. And that reason is actually more significant than the fact that the collisions are more frequent. So in terms of phrasing this in the exam, all right, more frequent collisions, the word frequent is your nod to time, which makes it suitable for rate. And then I'm also going to say more particles meet the activation energy, so you get a higher proportion of successful collisions. Now be careful the way you phrase this. I can't say I've got more successful collisions, because ultimately they both produce 50 centimeters cubed. So let's just say the magic number is 1,000 successful collisions in order to get 50 centimeters cubed. At high temperature they hit 1,000 after 2 minutes, but ultimately at 20 degrees I'm still able to get to the same number of collisions. It just takes longer, and that has to be reflected in your answer. So more frequent collisions, not more collisions, and here a higher proportion of successful collisions means I get there quicker, but the number is ultimately exactly the same. Other thing I wanted to very quickly touch on was catalysts. Catalysts lower the activation energy. So I've drawn a reaction profile diagram here for an exothermic reaction. Activation energy goes from the reactants to the top of the hill. And if you add a catalyst, it finds an alternative route with a lower activation energy, and this is going to massively speed up the rate of your reaction. So again, if we have a look here what a catalyst will do, no catalyst versus catalyst, you can see that the rate is faster, which is shown by my steeper line, but again the yield is the same. You will make the same amounts of product, you just make it quicker with a catalyst. Now the reason I want to point out catalyst is the only thing that you can't say you've got more frequent collisions. So this is my catalyst versus no catalyst, and I'm saying in both cases the collisions are 100 collisions per minute. So if you're talking about concentration, pressure, temperature, surface area, you can say they increase the frequency of collisions, but a catalyst does not do that. What a catalyst does do is it increases the frequency of successful collisions. So over here, maybe only 20% of these collisions resulted in a reaction, whereas over here 90%. So I don't need as many collisions to get to my desired yield of product, to get to my 50 centimeters cubed, because more of the collisions are actually resulting in a reaction. So again, just make sure you make that distinction. You've got a higher proportion of successful collisions because that activation energy is lower, but you can't say more frequent collisions. The final thing I wanted to say about rates is if you're asked to calculate it using a graph, all right, if they ask you for the average rate or the mean rate, if you see either of those two words, okay, then you do not have to draw a tangent. If they're saying the average or the mean rate after 2 minutes, then you go to 2 minutes on your x-axis, you go up to where it hits the graph, whichever graph they want you to go to, then you go across and you get a y value, let's say it's 40 centimeters cubed, and then you do y, which is 40, divided by x, which is 2. So no tangent needed, you just go up across and then do y divided by x. It's only if they ask you at 2 minutes that you draw a tangent. So look out for the words average and mean. Right, that's rates done. So do questions 1 to 5 on page 44, which is rates. 1 to 5. All right, how do you measure the rate? I've gone for gas syringe, but you equally could have gone for mass balance. Just make sure you're mentioning time. It's change over time. Disadvantage of each method: gas syringe, some of the gas can escape before you get that bung on. And mass balance, because the decrease will be so small, you just need a very sensitive balance, a balance with a high resolution, or you're not going to be able to record your results. Explain why rate increases as temperature increases. So these are 3-mark questions. Particles have more energy, so move faster and collide more frequently. All right, that will be 2 marks. But for your 3rd mark, more particles meet the EA, is just shorthand for activation energy. So more particles meet the activation energy. So I've got a higher percentage of collisions are successful. Don't say you've got more, you've got a higher percentage of collisions are successful, so you get to your endpoint a bit quicker. Explain why the rate increases in the presence of a catalyst. A catalyst lowers activation energy, finds an alternative route. So again, you've got a higher percentage of collisions are successful. So you don't need to go through as many collisions because more of them result in a reaction. And the last one I didn't talk through, but I just wanted to point it out. It just tends to come up all the time. Reactions slow down over time. Why? Tell me that the concentration or the number of particles is going to decrease over time, and if it decreases, you're going to get less frequent collisions. Right, we've done electrolysis recently, so I'm going to do this nice and quickly. Your core practical is using copper sulfate aqueous as an electrolyte, but you've got two different situations. You've got graphite and you've got copper as your electrode. For each, you're going to need to be able to predict what's happening at the anode and the cathode, and also what happens to the colour of the copper sulfate. Let's start here with our graphite electrodes. So the positive ions are going to go to my cathode and the negative ions will go to my anode. And you need to remember at the cathode that is always reduction. Just remember the two constants go together. Cathode is always going to be reduction. So the things at the cathode are Cu2 plus and H plus. You need to decide which one is going to be reduced. Because copper is more stable than hydrogen, copper is the product that will form. And you write your reduction half equation. Because it is a solid, you're going to see a build-up of solid around the cathode, and the cathode will ultimately gain mass. At the anode, you've got two negative ions to choose from. It's always going to be oxidation. You need to decide which one will be oxidized. It's always going to be your OH minus. The SO42 minus is never discharged. It's going to be OH minus, and this is the equation that you really need to learn. Okay, OH minus minus 4 electrons going to O2 and H2O. That's a gas. You're going to see bubbles. In the test that I gave you, they started this equation for you, if you remember, but they had the electrons on the other side. So you do see that the electrons are written as a product in an oxidation half equation. And if I bring the electrons to the other side of the arrow, just like in maths, the sign has to change. It's going from minus to plus. Now these equations are exactly the same. It doesn't matter which one you write, but just be aware of this in case they kind of give you the start of the equation so you don't get thrown off. That's the cathode, that's the anode, and then copper sulfate is your electrolyte, and copper sulfate is blue. Now the reason it's blue is because of the Cu2 plus ions, and if we see from my half equations, I'm starting with a Cu2 plus ion, but I'm turning it into copper. That's what's happening at the cathode. At the anode, copper is not involved there at all. So I'm losing Cu2 plus, I'm not gaining Cu2 plus, and that means the blue color is going to fade. The Cu2 plus will decrease, and as it decreases, that blue color will fade. Okay. Now all of this is happening because graphite is inert. It's not getting involved. So all you have to look at is the copper sulfate and the H plus and OH minus from the water. Graphite doesn't come into it. But when we go over here and I use copper electrodes instead, copper is not inert and copper does get involved. So when I'm looking at the cathode, instead of just asking myself H plus versus Cu2 plus, I'm now asking myself copper versus Cu2 plus versus H plus. In terms of what's reduced, it is still going to be Cu2 plus. Okay, exactly the same half equation as what we saw before, exactly the same outcome. You're going to get this build-up of copper around the cathode. At the anode though, this is where it changes. You've got copper, OH minus and the sulfate ion. Which one is oxidized? It is the copper. Okay, copper metal can lose 2 electrons to form Cu2 plus, and because you're losing the copper, you lose mass from the anode. Also, you're going to get a change. Sorry, you're not going to get a change in the colour of the electrolyte. Cu2 plus causes the blue colour. I'm making Cu2 plus at the anode. I'm losing Cu2 plus at the cathode, but the number is exactly the same, and therefore the electrolyte stays blue. The other thing you need to be aware of is they ask you what you do to the electrodes before and after. And it's really important that you read the question. If they ask you what you do to the electrodes before, that's when you use your emery paper, which is like a nail file, and it just makes the electrode super smooth. It removes all the kind of grease and impurities, and it allows the copper to adhere to the cathode and build up around the cathode. So you use your emery paper to make it nice and smooth before electrolysis. Now after electrolysis, if you came along with your emery paper, you just knock all the copper off, which is not what you want to do. Okay, you need to get the mass of it at the end. So afterwards you're going to be very gentle, and you're just going to rinse it with water, and then you're going to pat it dry or allow it to dry, and then you'll get the mass. You won't get the mass while it's still wet, because you don't want the mass of the water to be added to the mass of the cathode. You just gently rinse it and then you pat it dry. Your other option is to use propanone, which is a solvent. It will rinse it, and the advantage of propanone is because it's got a really low boiling point, it will evaporate quickly, so it makes it easier to dry. You wouldn't even need to pat it dry, it will just evaporate. Right, have a go at doing questions 6 to 10, please. Alright, in 6, because I've said graphite electrodes, this is your equation at the anode. You could write it the other way and have the electrons on the other side. But as soon as I switch to copper electrodes, you'll see the cathode equation is still exactly the same, but the anode equation has changed because the copper can get involved. In terms of colour, at the graphite, the blue will fade. We are losing Cu2+, but we're not gaining any Cu2+. But with the copper electrodes, because we lose it but then gain it, the Cu2+ remains constant, and the colour will remain blue. In question 9, what do you do before electrolysis? You clean them using emery paper, and you're doing that to remove impurities, and then after you're going to very gently rinse them with water and pat them dry. You could also use propanone. It is easier to dry because it's got a low boiling point. Alright, that's that.